Hey, nice to have you back. Um, Today we're going to be talking about graphs again, and got a couple of drawings to do. So I'm going to switch over here to the drafting area. Turn on the drawer. Uh, we're going to start with Planarity on page 634. Hope you got your book ready, like usual. Um, Planarity is all about being able to draw something in the plane. Planar. Planarity. Okay? And he starts with a little simple example. Uh, in the margin, figure 1052 has two graphs, G1 and G2, and they look similar, could be isomorphic, right? But um, ABCD on the left, G1, has a crossover on it that have to be there. Well, no. If we take and flip C up here, and it connects to A here, which goes across to B here, and then that goes up to C. C is kind of small now. And then we leave D down here where it was at. Okay, just flip C up, then we've got a planar embedding of that graph, right? He draws it a little differently in figure 10.3 in the main column of text. He flips A and B around as well. Not completely sure why he did that, but you know, to each his own, I suppose. And then he explains what a planar graph is, but we already talked about that really quickly. Um, then he's got an example, and this is a classic example. It's called the utility graph. The bottom of 634 there, and it connects electricity, gas, and telephone utilities to several houses. Um, three houses to three utilities to make it interesting, I suppose. And you'll notice that there's a house with a chimney, a house with an antenna. How archaic, right? And then SpongeBob's house on the right. Not really sure why SpongeBob's in this neighborhood, but you know, gotta live somewhere. This would normally spark about a 5-minute conversation in class, but we'll just move on. Hopefully, you SpongeBob fans get the joke, and those of you who aren't SpongeBob fans, you won't have to listen to us prattle for 5 minutes, right? Okay. Now moving up, we recognize first off that this graph, the utility graph, is K33, right? It's got three things on one side, three things on the other side. They're all connected in all possible ways, but it's bipartite. So we don't connect between the houses and we don't connect between the utilities. I know the gas company needs electricity too, but we're not worried about that right now. Okay. Um, Top of the next page, he talks about K5 as well. Reminds us of what K5 looks like. It's a pentagon with a star inside, so it's got all possible connections from all the vertices. And the next two theorems tell us that K5 and K33 are non-planar. For the proof of K5, he takes you to an pair of exercises, but for K33, he actually does the proof for you there, and it's not too horrible to follow. So I'm going to let you read over that on your own. And on the next page, K 636, I was going to give you a graph name again. On page 636, we have a definition for elementary subdivision of an edge. Basically, as the diagram on the left shows, you just add a node in the middle of the edge, and boom, you've subdivided it, right? Divided it into two pieces. No big deal. What does that give us? Well, it gives us the ability to form homeomorphic graphs. Okay, the very bottom of 636, it defines homeomorphic. Two graphs are said to be homeomorphic, if they can be derived from a common ancestor using only a sequence of elementary subdivisions. So as long as you just do some elementary subdivisions, putting an extra vertex in the middle of a edge, then you can be homeomorphic. And on the top of the next page, he's got a couple of homeomorphic graphs. And from my understanding, not only is the left graph with the diamond in it and the right graph with the triangle in it homeomorphic, but they're homeomorphic with their ancestor as well, because the ancestor is derivable by a sequence of 0 subdivisions from itself, right? So that's my understanding, is that they're all three homeomorphic to one another, not just the bottom two graphs with the diamond and the triangle. Okay. And what's so important about homeomorphism and elementary subdivisions? Well, they are used in Kuratowski's theorem at the bottom of 637. Graph is non-planar if and only if it contains a subgraph homeomorphic to either K5 or K33, the two graphs we proved non-planar earlier. Well, if you did your exercises. So we've got, sorry about that, still haven't figured out how to turn that off. And looks like I'm going to need to soon, because as you noticed on the website, I'm sure not mine, but the Harper website, we're going online starting April 13th. So this flexible learning thing is going to continue to full online to the end of the term, and apparently even into the summer. So social distancing is a fun thing, I suppose, for everybody, and we just have to have more of it. I don't know. Anyway, back to Kuratowski's theorem. Kuratowski said, you're non-planar if and only if you have a subgraph in there that's homeomorphic to K5 or K33. And he gives an example on the top of 638 with the line graph of the Königsberg graph. Remember that horrible thing? Yeah. And he finds in there not only a K5, but a K33. Okay. I don't even think there's really elementary subdivisions involved. It's just subgraphing. Okay. But then he gives an example with elementary subdivision at the bottom of the page. Again, 638, in case you're lost. Because I know I get lost in a lecture like this. And this one involves a K5 that has some elementary subdivision. Okay? So, and he says it's helpful to have a program that allows click and drag manipulation on graphs. That would be your full-on Mathematica. I don't believe Wolfram Alpha is going to let you actually click and drag on the images that it creates for you with the drawing solution we found the other day. Name's not coming to me now. It wasn't just graph, it was something graph. That bothers me. Doesn't it bother you? I feel like I have to go find it. Hang tight. I don't think I have it open right now, so let me go find it. Math 220. Representation notebook. Load Mathematica real quick. Adjacency graph. That's what it's called. And here you could click and drag these things, I believe, to change the points. You can certainly resize it. I thought you could move them around too. Maybe I'm not clicking right. Change the look of it a lot. That's not it, not layout. Maybe if I convert it to graphics. I don't know. I swear there's a way to grab these and drag them around. Because I swear I've done that to a regular graph, and I know it'll do it to this one too. I'll try to investigate that and I'll get back to you. I didn't have a chance before today, so. But, sorry, it's been really busy. I'm almost done grading your exams. By the way, I know you're listening to this next Monday or thereafter, but I actually recorded it this Tuesday. Today's for me the 31st. You might notice on my clock up there. So I'm got to record them ahead of time, and then I record the response videos right after I get your discussion input. Okay, so those will be more timely than the actual lectures. Just to let you know. Okay. But I'll try to find you that tool that I was talking about for manipulating the graph. Assuming you can get a student a version of Mathematica to play with that if you're interested. If you're not, then don't worry about it. It's not like I'm making you buy Mathematica. I just think it's a really awesome tool, and I know I enjoyed my student version of it when I was undergrad. So, but then I loved exploring all kinds of programming opportunities, and Mathematica has one of the most beautiful programming languages ever invented. Just ask Stephen Wolfram; he'll tell you. He's no slouch at self-aggrandizement. He'll tell you the way he thinks it is. Anyway, that's enough of planarity. You got K5, you got K33. They're non-planar. If you've got a part of yourself that looks like K5 or K33 with just elementary subdivision, no added edges or anything, then you're non-planar too. Okay. Regular polyhedra on 639. This is pretty cool. It reminds us what a polyhedron is if you haven't had geometry in a while. It's a closed surface in 3 dimensions. And a regular polyhedron has every vertex with the same degree and faces all congruent to one another. Congruent mean that they're similarly shaped, right? So they're all triangles, or they're all squares, or they're all whatever. And then he talks about, in example 1030 at the bottom of the page, a planar embedding of the cube. You just take that cube and you take the top and shove it down really hard, and the bottom, of course, breaks open and flies out. Sorry, I almost destroyed my book there. Trying to demo the motion that I wanted you to visualize, but you can't see. So but I can't draw it either. I really can't draw that. So I could barely draw that embedding earlier. So, but the planar embedding of the cube is pretty cool. It turns into trapezoids. The sides turn into trapezoids, and the bottom and top are still squares, but it's pretty cool. And this kind of thing leads to the idea of regions. How there are 6 regions in this planar embedding. The square in the center is a region. The 4 trapezoids are regions, and then there's everything outside of the embedding is the 6th region. Okay. And Euler's formula connects these things. It says that if you've got epsilon edges and n vertices as usual, then rho, the number of regions, is going to be epsilon minus n plus 2 at all times. Okay. And he's got a proof of that, which is a little involved, but I think it's followable. People have followed it in previous semesters. I think you can handle it. If you have any trouble, just let me know, and I'll talk you through it in an email or make you a video and post it on the website so everybody can see it in case somebody else is confused and not wanting to ask. Whatever works best. Okay. But then it leads us on the bottom of 640 after the proof of that last theorem to the 5 regular polyhedra, and got your epsilon, n, and rho again, but we also have the common degree of the vertices, d, and the number of edges bounding each face, because they're all congruent, so they have the same number of edges bounding each face, and that's b. And there are exactly 5 regular polyhedra. There can't be any more, and there aren't any less, of course, because we have at least those 5. But there can't be any more, and he's going to prove that shortly. There's a tetrahedron, which is pictured on the next page, 641 there at the top. It's all triangles all the time. It's kind of like a pyramid with a triangle on the bottom instead of a square. Cube, of course, we all know what a cube looks like. Octahedron is 2 pyramids attached at the squares. A dodecahedron has 12 sides. Decahedron would be 10-sided. Dodecahedron adds 2 to that. I'm not sure where the do comes from, but there's so many prefixes that we borrow from Latin and Greek. It's ridiculous. And then an icosahedron, I think we talked about it before, the Icosian game, is a 20-sider. Okay. And he shows planar embeddings of all of those on the right column of the figure. Very nice renditions, and you can see they all embed quite nicely in the plane. And then he talks about, in the proof of the theorem, why there can only be those 5. And it's a straightforward algebraic proof. It gets a little bit tricky at the end, showing that only 3, 4, and 5 can solve the equation. And at any given time, B or D has to be 3, and then the other one can range from 3, 4 to 5. And that's it. There's no other integer values that work. And they have to be integer values, of course, because those are numbers of things. You can't have 3.5 edges on a bounding face or a degree of 4.27, right? That's just insane. So follow along with that if you can, and if you have trouble, let me know. That leads us to chromatic number, and chromatic number is all about coloring maps, but we do it on graphs. And graphs, since we want to color a region of a map, we're actually going to take the dual of the map. And the dual turns every region into a vertex and draws an edge between two of its vertices when there's an edge bounding the two regions. Okay, the two regions share. So he gives an example at the bottom of 643. Yeah, we made it all the way to 643 now. I'm sorry, I didn't keep calling off pages every time we flipped. Sometimes I'll do that, just out of habit. And you can see two different embeddings of the same graph there in the example on the bottom of 643. And he draws their duals on top of that. It's a little hard to follow along, but you can kind of see where he's going with that. I would try to draw one myself, but don't think I can very well. Let's try to draw the dual of this one we have on the screen right now. Let me pick a different color so you can see it better. What, blue? Okay, let's do some blue. And the dual, we would have a dot here, and a dot here for the two inner regions, and a dot outside for the outer region. And there's an edge here between those two regions. There's an edge here between those two regions. There's an edge here between those two regions, an edge here between these two regions, and an edge here between those two regions. And so we end up with a graph with three vertices and 1, 2, 3, 4, 5 edges. Okay. Does that make a little more sense, having seen it demoed? Kind of glad I left that up, so I had a nice graph pre-drawn for that. But that's the dual, and that takes a map that has countries and whatnot, puts a dot in each one, and then if they share a border, we connect with an edge. Okay? And that's how we get a graph from a map. And then to color the graph, on 644, we talk about the chromatic number of a graph. Okay, and to color a graph, we color the vertices. Okay, and the idea of a proper coloring is that two adjacent vertices have different colors. Okay, every pair of adjacent vertices has different color. So we use Greek letter chi to represent the chromatic number of a graph, and we usually put a parenthesis G for telling which graph we're taking the chromatic number of, but if the graph is obvious, then we just say chi instead of chi of G. Chromatic number of a bipartite graph is easy. It's 2, because you just color all the ones in one set with one color. They never connect, so you can color them all the same color. And everything in the other set, the second color, because they never connect to each other. And then the adjacent vertices are always different colors. So bipartite's easy. But normal graphs, can be arbitrary and can get different chromatic numbers. So along came the 4-color theorem eventually that says the chromatic number of a planar graph, and it has to be planar because our maps are planar, right? We don't have non-planar maps. Think about that for a few seconds before you move on. Give the film a pause. And the proof, unfortunately, of the 4-color theorem is ridiculously hard, but it is true. Okay, they've proven it. You can believe them. But the chromatic number of a planar graph is at most 4. You don't have to have more than 4 colors to color any planar graph. Now, on the way to the 4-color theorem, we had the 5-color theorem, which is easier to prove, but needs a little help from theorem 10.4. 10.4 says that if you got a connected planar simple graph, then G has at least one vertex W with degree less than or equal to 5. That's a pretty bold statement, really. Connected planar simple graph. That's pretty low restrictions, really. But it'll have at least one vertex with degree less than or equal to 5. That's crazy, right? Well, he puts together some different theorems and propositions we've had before and comes up with that value. And it does a proof by contradiction. So follow along that and let me know if you have any trouble. That's at the bottom of 645, by the way. I forgot to update you on the page. I got to get better at this. And then comes the proof of the 5-color theorem. And it takes him 2 pages with supporting diagrams. So that one's really hard. I would not hold you to that one at all. Okay? Don't even concern yourself with that one. Then we've got the exercises on 648. A couple of nice, nice proposition and an interesting and useful definition there. Some nice graphs in this section, taking duals and proving planarity and stuff. So check those out. And I think that's a good wrapping up point for this lecture video. We'll dive in on 651 to directed and weighted graphs after a couple of questions. Okay, we'll have a couple of questions on what we just talked about. Remember, they're graded 20% correctness and 80% participation, so make sure you participate within the week that you've got to do this. Because after a week's over, you can't participate in the questions anymore, and that part of your grade's gone. All right? It goes into the in-class portion of your grade. So that's a bad thing to lose. I can't remember what percent it is off the top of my head, but let's see if we can find it real quick in the syllabus here. In-class activity is 10%. You don't want to lose that 10% because it's active now. We have to have this participation portion of our interactions now. So okay, we're still in graphs. It's a long section, but we're on our long chapter, but we're on the last section. So hopefully we can finish directed and weighted graphs in the next lecture video, and then we can move on to trees. And that chapter is much smaller. It's only got 3 sections we cover. We're skipping 11.3 because it's very application oriented. And they're neat applications, don't get me wrong, and you could possibly do some programming exercises from that if you wanted to for extra credit, but they're beyond the scope of a math course, okay? And this is, a driven math course. So, all right. Let's pause here so you can answer some questions, and I'll see you in a few minutes.